Okay, cool. So this video is going to look at how we can harness the power of a spreadsheet to help us collect, process, and transform data in a physics experiment. This is aimed at level 3 physics NCEA. And what we're going to do is use Excel in this example, and the main reason for that is that I haven't worked out how to make Google Sheets produce error bars that are going to serve our purposes, and so this is all going to be based on Excel. You might set up your results table to look something like this, with your independent variable down the left hand column and your dependent variable repeated to the right of it. In this case, we're thinking about a light bulb, measuring the light intensity as we move different distances away from the light bulb. So your raw data might look something like that, with uncertainties recorded just for the distance. So the real power of a spreadsheet is that it lets us do a whole lot of calculations really quickly by applying one rule to all of our data. And the way we tell the spreadsheet what to do is type into the function bar right up the top of the screenshot there. You can see it says equals average, and then I opened a bracket and I just highlighted the three numbers that I wanted to calculate an average for. Those are the ones that are associated with the distance of 0.5 meters. And when I hit the enter key, that's going to calculate the average for me. I can then train the spreadsheet to apply that same rule to all of my data by just clicking the bottom right hand corner of the box where it's got a little square and dragging that down, and that's going to cause the spreadsheet to average all of my data rather than just that first row of data. Hopefully it's going to look something like that. You can see as I've dragged it down, it's spurted out averages for every single one of my pieces of data. The thing we're going to look at next is how can we work out how much is the uncertainty on that average. And the way we're going to do that is by calculating the difference between the average and the piece of raw data furthest from it. We can get Excel, or whatever spreadsheet you're using, to help us do this. And the best way that I've worked out of doing that is calculating that difference between the average and each column of raw data, and doing that for each column of raw data. So you can see I've called it uncertainty #1, #2, and it's meant to be #3. And the function that I'm using to calculate that difference is the equals ABS value. That's the absolute value function, which is always going to return a positive value. We don't want a negative uncertainty, and so the absolute value just tells the spreadsheet to make the answer positive, whatever it is. And that's because the piece of data could be above or below the average, and this will solve that problem for us. And we're just going to do exactly the same function for the next column of data and get the spreadsheet to apply it to that column. And then for each column, as we do it, we're going to drag it down so it applies it to all of our data. Once we've applied that rule to each of those three columns of data, what we want to do is get Excel to pick out which one of those three columns has the greatest value in it. And that's because the uncertainty, we always go for the worst case scenario, the greatest uncertainty. And so the function that gets the spreadsheet to do that for us is equals max. That picks out the maximum of those three values. So equals max, open brackets, and then highlight those three pieces of data, and then once that's done, drag it down, and the spreadsheet will have chosen the worst case scenario for each of our columns of data, which is generated for us a column that is the uncertainties in our average value. That's how we've generated uncertainties, through the repeating it and averaging process. rounding the uncertainties. We can only justify stating uncertainties to one significant figure, and so we have to round up all of those uncertainties to one significant figure. Unfortunately, the spreadsheet only seems to round to decimal places, and so when we use the equals roundup function, we type in equals roundup and click the number, the unrounded uncertainty that we want the spreadsheet to round up, and then comma, and then how many decimal places we want to round it to. We just have to work it in our head how many decimal places that needs to be in order to make it one significant figure. Now we've got to round the average value so that it matches the same number of decimal places, the same place value as those uncertainties that we just rounded. And so the easiest way of doing that is using the round function. So equals round, then open brackets, click the thing you want to round, and it's just going to round it normally for us rather than automatically rounding it up, comma, and then the number of decimal places that you'd like it rounded to, and just choose that number of decimal places so it matches the same number of decimal places as there was in the uncertainty that you just rounded previously. Right, so that's the processing done. Now we're on to transforming our data so that when we plot it, it produces a straight line graph. And the way we're going to go about that in this is to use the log-log technique. And if you have a look at the other video, that's going to explain how the log-log technique works. To log something, we're going to use natural log, so equals ln, and click the thing we want to log. We're going to just start by logging all of our distance values, and then because of the way that logs compress numbers, we're going to have to take the log of the distance plus the uncertainty and the log of the distance minus the uncertainty, and that's because logs compress big numbers more than they compress small numbers, and so even though the uncertainty is fixed, it isn't going to have a fixed effect on our logged value. That's why there's so many columns. Here goes our first hidden uncertainty, and you can see I've put equals log, and then as well as clicking the distance value, I've put plus 0.002, which is 2 millimeters converted to meters. That was the uncertainty that I had on the scale I used to measure the distance, and so I'm just adding that on to each of those values. Same thing, but now we're going to go the distance minus 0.002, and what you'll notice is we don't get a constant difference between the logged distance value and the distance plus uncertainty and distance minus uncertainty. They're going to be subtly different. Now we're going to go through exactly the same process, but we're going to do it for the illuminance values, the brightness of the light. And you can see I've gone equals ln and I've clicked the rounded average value. We're going to work the plus and the minus through exactly the same as we did with the distance ones, but instead of having a constant fixed value, I'm just going to add on or subtract off that uncertainty that we calculated from our repeating and averaging. So you can see I've chosen the two cells that I want to use, and I've put the minus sign between them. Gosh, this next bit's complicated, so hold on to your socks. We're going to have to round our logged values, and the correct way to round our logged values is so that the mantissa, the number of decimal places on the logged value, is the same as the number of significant figures on the unlogged value. So looking at my distance values, almost all of them, except for the first one, were 4 significant figures, like 1.000. That's 4 significant figures, and so I need to make sure that the log of the distance and distance plus uncertainty distance minus uncertainty, are all rounded like that to 4 decimal places, except for the top one. That's only 3 significant figures, so only 3 decimal places. Next, we're going to do that same complicated rounding to all of our logged illuminance values, but now we've got to look back at our rounded averages, and we notice that there's not that many significant figures there, sort of 2 or 1 significant figure, and so we're going to round our logged values to be consistent with that to 1 or 2 decimal places. Very soon we're going to have a go at plotting a graph, but let's just get all of our calculations done while we're here. The last little thing we have to calculate is just how big is the difference between our logged distance value and the one that includes the uncertainty. How much is that up above and down below the logged distance value? And then same question for the illuminance ones, like how much is the difference between the logged illuminance and logged illuminance plus uncertainty? We need to calculate these because these are going to be the lengths of our error bars on the graph, which give us an idea of how much uncertainty we have in each of the points we're plotting. So you can see I've called them x error plus, x error minus, y error plus, and y error minus, and I'm using the equals absolute value function to calculate them. Scatter graph. That's the only sort of graph. So we highlight the logged distance and highlight the logged illuminance columns and click the little insert scatter graph icon, and that's going to plot up our data, and all going well, it should fall in a beautiful straight line because that's what the log technique should do. If it isn't, something has gone drastically wrong. We need to add our error bars onto our data, and so to do that, click the little plus up the top right hand corner of the graph there and go down to the error bars thing and choose more options. That's going to give us the opportunity to individually customize the length of every single error bar, and that's what I haven't worked out how to do on other spreadsheets. Format your little error bars so that they have lengths that are equal to the x error plus, x error minus, and y error plus and y error minus that we calculated earlier. And you should see that your error bars kind of have almost equal size on either side of the data point, but not completely equal. Add a trend line. In this case, I right-clicked my data and chose the Add Trend Line option. And looking at how that trend line fits, I'm not that happy with it because actually it sits outside of the error bars for quite a number of those points. And that point at the top left, it misses it completely. It doesn't go anywhere near it. So that shows me that maybe not all of my data, not all of the range of data that I've recorded follows the theory that I'm trying to fit it to. So maybe there's something happening either at very small values or very large values of my independent variable that mean the data doesn't quite fit the theory. So I'm going to try and make a better line that fits that data better. To add a better line on, what I've done is I've added another whole data set onto my graph, but this time I've chosen only the bottom 7 values. I've excluded the top 3 out of my results table, which represented the lowest values on the x-axis there. You can see the red ones are the new ones I've plotted, and those blue ones are the old ones that I haven't plotted. And so what I'm going to do is try and fit a new trend line just to those new data points that I have plotted, and what I'm hoping is that if I fit a trend line to those and ignore those 3 blue points over on the left-hand side, that's going to give me a better fit to the data, and hopefully that trend line is going to go through all of those red data points really nicely. And there it goes, and I'm much happier with that trend line than I was with the others. It's kind of a clue to me that something's happening at really small values of distance. So remembering that this experiment was looking at the illuminance, the brightness of light, and how that changed as we moved away from a light bulb. So what this is showing me is that my experiment didn't perfectly match my theory when I was really close to the light bulb. Something's going on there. You can see that I've added an equation to each of those different trend lines, and that's given me both the gradient and the y-intercept for each of those lines. I've called my original one the error line because I think that's a pretty good, worst fit of my data, and the new one, the red one, is the best fit line, and I've labeled it like that.